Hello, dear students. Welcome to the discussion of electrostatics. This is the eighth lecture of this series. In the last class, we discussed about electric field. We explained what is the definition of electric field. Then we derived the equation for electric field intensity at a point. In this class, I will explain what are electric field lines. Okay, electric field lines, or they're also called electric lines of force. Okay, so we studied that when a charge is placed at a point, suppose a positive charge, the the field here there is a source charge. We can call it a source charge. The charge produces a field around it, and to measure the field at this point P, we have to place a plus one coulomb charge here. Okay, if you place actually the what is the definition of electric field? It is a force acting on a unit positive charge placed at a point. That is why we are placing a plus one coulomb charge there. So when this plus one coulomb charge is placed at this point, what happens? This plus one coulomb charge will feel a repulsion from this positive charge because both charges are like charges, both are positive here. So this charge will experience a repulsion from this positive charge. Okay, if the plus one coulomb charge is placed at this point, it will experience a repulsion in this direction. If it was placed here, it will experience a repulsion in this direction, and so on. If it is placed here, it will experience a repulsion in this direction. So from this we can understand that around a positive charge, when we place a unit positive charge or 1 coulomb charge plus 1 coulomb charge, it will move away from this positive charge. It will move away from this positive charge. So these directions in which a unit positive charge would move, if it is free to do so, are called electric field lines. Okay, these lines are called electric field lines. Now I have drawn the electric field lines of a positive charge. Electric field lines of a, if you are asked to draw the electric field lines of a positive charge, you have to draw this diagram. Positive charge. Positive charge means the charge is greater than zero. Positive means uh, quantity is greater than zero. Okay. Now, how can we draw the electric field? So, I think you got the definition. Electric field lines. This is not a strong definition, but actually we draw the electric field lines around a charge. The definition is uh, for a definition you can use this definition, but the definition is not so important. It is defined as the electric field intensity. Sorry, electric lines of force or electric field line is defined as the path along which a unit positive charge would move if it is free to do so. It's a path along which a unit positive charge tries to move when placed at a point. Okay, suppose you have placed a negative charge. Suppose charge is a negative charge, and you want to draw the electric field of that. For that, you are placing a plus one coulomb charge here. What will happen to the charge? The charge will be attracted in this direction. If it is free, it will move in this direction. Suppose the plus one coulomb charge is placed here. What will happen? The charge will be attracted in this direction. If the plus one coulomb charge is placed in this here, it will be attracted in this direction. If it is here, it will be attracted in this direction, and so on. The plus one coulomb charge will be attracted in this direction. Sorry, yeah, the plus one coulomb charge will be attracted in this direction. Here, if it is placed here in this direction, if it is placed here in this direction. Okay, so this is how we draw the electric field lines of a negative charge. Negative charge Q less than 0. Okay, So we draw the electric field lines on the base of the definition of electric field intensity at a point. What is the definition? Do you remember the definition of electric field intensity that I have discussed in the last class? Electric field intensity at a point is defined as the force experienced by unit positive charge placed at a point. It is a force experienced by unit positive charge placed at a point. Okay. Now we have to draw the electric field lines of a dipole. This is the third diagram, the first diagram, second diagram. Now we are going to draw the electric field lines of a dipole, an electric dipole. What is an electric dipole? Dipole means there are two poles. Which are the two poles in electrostatics? Positive pole and negative pole. So an electric dipole is two equal and opposite charges, or a positive pole and negative pole separated by a very small distance. A positive pole and a negative pole separated by a very small distance is called an electric dipole, like molecules. For example, if you consider HCl molecule, you know it is a covalently bonded molecule, but because of the difference in the electronegativities between chlorine and hydrogen, what happens is that the shared electron, since it is a covalent bond, one pair of electrons are shared in between hydrogen and chlorine. Because of the difference in electronegativity, you know chlorine is more electronegative than hydrogen. So what happens is that the electron pair shifts towards chlorine. So chlorine becomes partially negative and hydrogen becomes partially positive. Now this hydrogen chloride molecule or HCl molecule is a dipole, because at one end it is positive and the other end it is negative, and it is separated by a small distance. Actually, you know, the bond length of molecules is in the order of angstrom unit. Angstrom unit. That is very small. You know, one angstrom unit is 10 raised to minus 10 meters. So it is very small. So usually molecules are examples for we usually call the polar molecules. Polar means the poles are separated. Polar molecules are examples for electric dipoles. Okay. Now we have to draw the electric field lines of an electric dipole. How can we draw the electric field lines of an electric dipole? Electric dipole means a positive charge and a negative charge separated by a small distance. So how will we draw the field lines? It is like this. The pleasant Coulomb charge, when placed here, it will be repelled from positive charge and it will be attracted by the negative charge. If it is placed here, due to repulsion, it will move like this, and then it comes to the attractive region of the negative charge. So its motion will be like this. So altogether, if we draw the field lines, we will get a set of lines like this. Okay, the field is attractive here. The field is attractive. That is why it bends towards the other charge. When you put arrow on the side of negative charge, you have to put the arrows like this into the charge, because field for a negative charge, the field is into the charge. For a positive charge, it is away from the charge. So you have to be careful. Yeah, like this. Okay, this is how to draw the field lines of an electric dipole. Okay, now suppose there are a pair of positive charges or a pair of negative charges. A pair of positive charges which are very close to each other. In that case, how can we draw the field lines? You know that there will be repulsion between these two charges. There will be repulsion. So how we draw is like this. The field is repulsive. It bends away because of repulsion. It bends away because of repulsion. Yeah, field should be drawn like this. Here also the copy of that. The field bends like this. Okay, so what is a field in between? Suppose you draw a line between these two charges. What is a field at this midpoint? Actually, the field at the midpoint is zero. Electric field at the midpoint is zero. So this point is known as null point. Null point. This point is known as null point. Okay, that point is known as null point. If you draw the electric field into a pair of negative charges, the only difference is that you should put the arrows into the. If these two are negative charges, you should put the arrows into the charges. That is only difference. Okay, so you can draw the field due to uh, a pair of negative charges like this. This is a minus charge, this is a minus charge. The field between them. Again, here there is a repulsion, but the arrow should be inside. Yeah, the force is repulsive, but the arrow should be inside. Okay, like this. Oh, this should be inside. Okay, like this. The only difference between this diagram and the diagram of two positive charges is the arrows are towards the charges because they're negative charges. Okay, so this is how we draw the electric field lines. Now we will discuss the properties of electric field lines. Properties of electric field lines. It's a very important question. You will be asked to write two, three, four properties of electric field lines. Okay, here I have written 8 points, 8 properties of electric field lines. First one, as we have seen, suppose there are two charges, like one positive charge and the other negative charge. How can we draw the electric field lines? The field will start with the positive charge and it will end at the negative charge, like this. Okay, the electric field lines start at positive charge and end at negative charge. Suppose there is only one positive charge, what will happen? It's an isolated single charge. Isolated single charge. Field will go away to infinity. That will in go to infinity. It is like this. You have to draw the field lines away. If there is no negative charge, the field will go to infinity. The if it is a negative charge, what will happen? If it is an isolated negative charge, I mean separate negative charge, what will happen? The field will come to the charge. The field will come to the end at the charge by starting at infinity. The field will start at infinity and end at this charge, right? The field will start at infinity and end at this charge. So read this part. For an isolated single charge, electric field lines start or end at infinity. The electric field lines start infinity for negative charge and it end at infinity for positive charge. Okay, so you got the sentences. First property, you understood the first property. Okay, now the second property, in the charge free region electric field lines have no break or they are continuous. Suppose this is a charge, this is a negative charge, one positive charge, negative charge, the field will be continuous from this to this. There will not be any breaks in between, like it cannot be like this, because here there is no charge. If there is a charge, it can be like this. Okay, suppose there is a positive charge or a negative charge placed here, so the field can be like this. But if there is no charge, the field will be continuous like this. Okay, there will not be any breaks in a charge free region. Electric field lines have no break or they are continuous. The third one is more important property. Two field lines will never intersect each other. Two field lines cannot cross each other. Two field lines cannot cross like this. This is not possible. Why this is not possible? I will explain the reason after discussing. Uh, I think it is the fifth point. Okay, then only I can explain why two field lines will never intersect each other. So now understand that the field lines will never cross each other. Okay, in a uniform electric field lines are parallel. So what is uniform electric field? Electric field is uniform. Uniform means it's constant everywhere. If you consider positive charge, you know the equation for electric field. It is equal to 1 by 4 pi epsilon 0 q by r square. So this field is inversely proportional to r square. That means as r increases, what happens? Electric field decreases. If you draw the graph, it will be like this. Okay, and the graph will be like this. It will meet the axis at infinity, e proportional to 1 by r square. Okay, so the electric field is decreasing with the distance, so it is not a uniform electric field. Uniform means constant. How can we produce constant electric field? Actually, constant electric field is found, as I have discussed in the previous video. Suppose you have a positive plate like that of capacitor and a negative plate, large positive and negative plates. Then in between the plates there will be electric field like this. They can be drawn as parallel lines. Actually, parallel and equidistant. Parallel and equidistant lines. Equidistant means the lines are at equal distances. Okay. Uniform electric field. In a uniform electric field lines are parallel, and you can write parallel and equidistant. Okay. Parallel and equidistant. So the electric field lines can be drawn like this. Now coming to the fifth point. The number density of electric field lines at a point gives the strength or intensity of electric field at that point. I will explain that. Suppose we have drawn the electric field lines of a positive charge. You remember the diagram. Okay. So this is the field lines of a positive charge. Now, if you consider an area here, there is suppose this is a circular area here. Through that area, you can count 1, 2, 3 lines are passing through that area. Suppose the area is 3 lines are passing. So the number density means number of field lines passing divided by area. So it is 3 per that area, 3 per that area. Okay. And if you consider the same area here, I'm considering the same area here, but only a single line is passing through it. So here, if we find the number density, it will be 1 by a only. So it is reduced to 1 by a. It was actually it was 3 by a, very close to this charge. When we move away from this charge, the number of field lines decreases. It is because when we move away from the charge, the field also decreases because field is inversely proportional to square of the distance. So when field decreases, the field lines becomes farther, okay, farther apart. Okay. When the field is stronger, the field lines are very close to each other. So the number density of electric field lines, number density means number by area here. Now, field lines at a point gives the strength of the electric field at that point. The number density of electric field lines at a point gives the strength of the electric field. That means if the number density is high, you can say that the electric field is stronger at this point. Suppose it is EA and it is EB. Here, you can say that EA is greater than EB. EA is greater than EB. Okay. Now coming to the sixth property. The tangent drawn to the electric field line at a point gives the direction of electric field at that point. So, you know, suppose this is a positive charge, this is a negative charge. And suppose there is a field line like this. Now, since it is a curve, how can you draw the direction of field at this point? You have to draw a straight line here, touching this point, which is called the tangent. You have to draw a tangent here. This will give the electric field at this point. Electric field, the direction of electric field at this point. If you consider this point, you have to draw a tangent here to get the electric field, direction of electric field at this point. You have to draw a tangent like this. If you consider the field line like this, you know, here the field line will be straight. That is same as the direction. There is no, if it's a straight line, there is no need to draw the tangent. But if it's a curve, there is, you should draw the field line, the tangent to get the direction of field line. So yet the tangent drawn to the field line at any point, at a point, it gives the direction of electric field at that point. This is a very important property. Okay, tangent will give the direction of electric field at that point. Electric field lines do not form closed loop. Electric field lines do not form closed loops. This is the seventh property. Electric field lines do not form closed loop. Means it cannot form a closed loop like this. This is not possible. Okay, I will explain why this is not possible. Before that, I will explain the second point, second or third point that there I said I will explain after the sixth property. Okay, so I will explain this first. Electric field lines never intersect each other. What is the reason? Suppose the two lines intersect each other. Suppose actually they will not intersect each other, but if we assume that they intersect each other, then at the point this point of intersection, suppose you draw the field line. How can you draw the field line at the point of intersection? How can you draw the direction of electric field at that point? Sorry. At the point, if you draw the electric field, I'll make it proper. It will be a tangent like this, tangent like this. Not a tangent like this. This is a one case. If you draw the tangent to the first line, it will be like this. And if you draw a tangent, so this is one of the directions of electric field at this point. Sorry. One second. Okay, that's okay. One of the directions. If you draw the tangent to the other field line, this is another field line, this is another field line. If you draw a tangent to this at this point, it will be like this. So since the two curves are meeting at a point, we have to draw two tangents. For the first curve, we got a tangent like this. For the second curve, we got a tangent like this. Okay, so when two field lines meet, what do we get? We get two tangents at that point, or we get two directions for electric field at that point. Suppose this is one of the tangents and the other, this is the other tangent. Okay, but this is not possible because electric field cannot have, electric field is a physical quantity, so it cannot have two directions at a point. It is never possible. So two field lines will never intersect each other. Okay, I think you got the point. If two field lines intersect it at a point, that means there are two directions for electric field at that point, which is never possible. So two field lines will never intersect each other. Now I will come to the last property, the explanation of the last property. Why electric field lines do not form closed loops? If, suppose they form closed loops, then what happens? There are two curves meeting like this. It is like two curves meeting because a single curve is meeting or a single curve is making a closed loop. But at this point, the if you draw, you have to draw the tangent to this curve, and you have to draw the tangent to this curve also. So there will be two directions for electric field at the point of meeting. So this is not possible. So two field lines, sorry, electric field lines do not form closed loops. Okay, so you got the points, the properties, seven properties, not eight. Uh, there are seven properties. So uh, you have to by heart at least three or four properties. Okay, so the field line start at positive charge and at negative charge. If it is a single charge or isolated charge, it will start or end at infinity. In a charge free region, electric field lines have no breaks or they are continuous. In a charge free region, electric field lines are continuous. The two field lines will never intersect each other. In a unified electric field lines are parallel and equidistant. And the fifth property, the number density field lines at a point gives the strength of the electric field. When the field lines are closer, electric field is stronger. The tangent brought to the electric field line at a point gives the direction of the electric field. And finally, the electric field lines do not form closed loops. Okay, we have already explained this question. Two electric field lines never intersect. Why? Okay, this is the answer. You can by heart this answer. I think you have got the idea. You have already understood this answer. If two field lines intersect at a point, then there will be two directions for electric field at that point. But this is not possible. So two field lines will never intersect each other. Okay. Now coming to another question. That's not a very good question, but uh, roughly you can say the answer. It's a conceptual question. Uh, Figure below shows the electric field lines for 2 point charges separated by a small distance. Okay, these are two charges. One charge is q1, other charge is q2. Determine the ratio q1 by q2. We are asked to find a rough ratio of q1 and q2. Actually, and the second part, what are the signs of q1 and q2? Looking at the field lines, you can say that signs of q1 and q2. Signs of q1 and q2 means whether they are positive or negative. In the case of q1, you can see that the field lines are moving away from q1, right? Field lines are moving away from q1. Okay, that means q1 is a positive charge. Q1 is positive. And what about q2? In the case of q2, the field lines are coming to that q2. That means field lines are coming to a charge means it is a negative charge. Q2 is negative. Okay, so we got the answer for that. Q1 is positive and Q2 is negative. Now, how can we find the ratio of Q1 and Q2? Actually, in this question, We have to count the field lines starting or coming to each of the charges to find the ratio. It is based on the property that the number of field lines gives the strength of the field. Number of field lines gives the strength of the field. If the charges are stronger, if the magnitude of the charges are larger, they can produce more fields. So if you find the ratio of these two charges, to find the ratio of these two charges, you can count the field lines. For the first, for Q1, how many field lines are starting from Q1? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 field lines are starting from Q1. And how many of them are reaching Q2? You can see only 6 lines are reaching Q2. Only 6 lines. Like, I will count from here: 1, 2, 3, 4, 5, 6. Only 6 lines are reaching Q2. So the ratio of the charges is the magnitude of the ratio of the magnitudes of the charges is 3, right? Okay, the ratio is 3. 18 by 6 equal. So this is the idea about the field lines. So we discussed the what are field lines. They are drawn along the path along which a unity positive charge would move. We have drawn the field lines for a positive charge, a negative charge, an electric dipole. Electric dipole means two equal and opposite charges separated by a small distance, then a pair of positive charges, then a pair of negative charges. You have to practice drawing these electric field lines. Then we discuss the properties of electric field lines. There are 7 properties. You have to by heart at least 3 or 4 properties. Then we discussed 2 questions. One question is, two field lines never intersect each other. Why? Okay, you understood the point. Then this question also. Okay, so I stop at this point. I think you got a clear concept about the electric field lines. In this, in the coming lectures, we will discuss about. In the coming lecture, we will discuss about electric dipole. I think that is the next topic. Okay, see you in the coming lecture. Thank you.